Hello, it's Ryan. I hope you're all well. This lecture is on a couple phenomena of light, reflection and refraction. We're going to start with reflection. Remember from our other video that reflection is the absorption and re-emission of electromagnetic waves. And really there are two flavors to reflection. There is specular reflection. Specular reflection and diffuse reflection. And really the best way to show these are with a diagram, and so that's what we're going to do. For specular reflection, we'll have a surface that the light is reflecting off of, like so. We'll have our incident light coming in all parallel to one another. And so we'll have it like that. And then what we can do is just kind of put a bunch of these on here. I ran out of room there. Okay, so there are our incident rays. I'm going to put arrowheads on them. So this is our reflective surface. Whenever we measure the angle that their light is incident, these are our incident rays. We're doing this in a geometric optics way because we're making the rays of light linear lines. And so anyway, these incident rays are going to be incident or collide with, be absorbed by, and re-emitted by this reflective surface. And the way we measure the angle of the incident rays is we first have to draw in a normal to the surface that the reflection is happening. And now from the normal to the ray gives us our incident angle, theta I. And so each of these will have theta I for an incident angle. And our light will be reflected like so. And the reflected angle is measured from the normal as well. And so we could note that theta I is our incident angle, and theta R is our reflected angle. Now I'll go a little quicker for diffuse reflection. Diffuse reflection is similar to specular in the sense that all these rays will be reflected, except now the rays will be reflected in all different directions. So I'll go ahead and make a few incident rays here. And 3 should be enough. And so we can go ahead and draw in the normal to the surface. But now the normal to the surface, if you can tell, the surface is rough. And so the normal is going to be on a different angle. And so we'll see that. So here the normal looks like it's about here. Here the normal looks like it's about here. And here it might be like that. That's our normal to the surface. And so we could show that we have incident angles, theta I, and now we can show the reflected light. And those have reflected angles. Okay, and so really after seeing this picture, you can see the two different styles of reflection, and both of these reflections or flavors of reflection depend on the law of reflection. And the law of reflection is pretty simply put. We know that no matter what, in any reflective on any reflective surface, that the incident angle I, theta I, is always equal to the reflected angle theta R. And it would be worth noting, you must remember that the angles are always measured from the normal to the surface. So don't measure your angles from the horizontal. That would be bad. And that is the law of reflection, and it always holds true. So another phenomenon related to reflection, I think it was number 5 or 6 on that list of phenomena that we had, was called TIR. TIR was total internal reflection. But I'm actually going to come back to this after so we will return. I just want you to know or remember that there were really two different kind of phenomena associated with reflection. Total internal reflection would be the other one that we would talk about. We'll come back to that. We need to discuss refraction before we can talk about total internal reflection. And if you recall, refraction was the bending of light when it goes or when it moves from one medium to another. So we could make a little bit more of a definition here. So we could say when light goes from a slower medium to a faster medium, it bends away from the normal. And the opposite would be true if it was going from a faster to a slower. Yeah, so it would move toward the normal if it was going from a faster to a slower. And so you might note that the opposite is true if you reverse faster and slower. So before I get any further along with reflection, we have to define for you something called the index of refraction. And the index of refraction is really what this slower or faster is implying. So in general, the index of refraction, we give it an N. An N. So N is defined as the index of refraction. And one way that we experimentally determine N is by measuring the apparent speed of light in different media. So remember, light travels at the speed of light, c, the speed of light, which is always 299,792,458 meters per second. And that's what light always does. Now, when we put light from air into water, let's say, light will appear to move slower. That isn't necessarily the case. Light always moves this speed, but what happens when light is going through a medium, through air or through ice or anything really, it gets absorbed and re-emitted by the particles that make up the medium. And so it's the absorption and re-emission time that adds to the time that the light is in the medium. It's kind of a lot to take in, but the reason I'm talking about it is because we would measure the apparent speed of light in a medium, and we would divide that, divide that by the speed of light in a vacuum. So N is equal to C over, I think I said that in reverse, V apparent. And so this is the speed of light in a vacuum divided by the speed, and I better not write that, I should say something, I should say the apparent speed of light in a medium. And so if light seems to move the same speed in air as in a vacuum, then we would say that N for air is approximately 1, meaning the speed of light that we would measure in air would be approximately equal to the speed of light. It actually, N for air, if I remember correctly, is 1.00029. And it's unitless, obviously. So often in our class, we'll use N for air just to be 1 because it's very close to 1.00029. So that's the index of refraction. And normally those are just known quantities given a medium, or we would determine what it is given some refracted angles. Okay, so refraction is the bending of light when it moves from one medium to another. And mathematically speaking, we'll draw it out next. We use something called Snell's law. Snell's law says that N incident times sine of the angle that is incident will always equal N refracted times sine of the angle that it is refracted at. So Snell's law is given by this equation, and it might be worth noting again that thetas are always measured from the normal to the surface, or the normal to the interface between media. That's N for the normal. So we'll do this diagrammatically. And what we might have could be an interface between water and air. So maybe this is the interface between water and air. And there may be sunlight coming in. I'm going to make sunlight orange just because it might be easier to see than yellow. And so sunlight might be coming along. And remember, this is just an approximation for the sunlight. We know that there are really more than one ray coming from the sun. But that would be our incident light. Once the light interacts or hits the surface between air and water, it will bend. And we normally would say that air is a faster medium than water, so this N air is out here. And then it's going, this is the interface between the water and the air. And so I'm drawing in the normal to the surface. And then, of course, in here we would have N for H2O. We'll say this is fresh water, so the N for fresh water, I believe, is 1.333. And again, we'll use 1 for air just to simplify this a little. So we know that the incident angle is measured from the normal to the surface. And because water has a higher index of refraction than air, we know that water is what we would call a slower medium. Water will have light appear to move in a longer time over the same distance that it would in air. And now our light will bend toward the normal, like so. So our refracted angle is going to be smaller than our incident angle, theta r. And so that is a diagrammatic representation of refraction, and we might note that the refraction is occurring at the interface. And we can kind of show that that's happening. Right there is where the light's actually bending. Something else that's happening, that always happens anytime we have light incident on a surface like this, is that some of that light will actually be reflected, and it will abide by the law of reflection, so it will have the same angle that it was incident. And so some of our light is reflected, and some is transmitted. So this is reflected light, and this is transmitted light. And we know that the total light, the total incident light, must equal the transmitted light plus the reflected light. It's not quite necessary, but it is important to kind of know. It makes some sense, doesn't it? The light can't just disappear. Light is really just energy. And we know that energy can neither be created nor destroyed, only transformed. So that's a diagrammatic representation of refraction. And now, if you can imagine, if we had control over where this sun is, if I could just take the sun and move it down this way, I would be increasing my incident angle. As I do that, I would also be increasing my refracted angle. And can you imagine that there's a point, if I could move this sun downward, there's a point where this refracted angle will equal 90 from the normal. This is the point that we would see total internal reflection. And so we're going to just finish this conversation or this lecture with our total internal reflection. Like I said, if we could change the incident angle, if we could increase it until this refracted angle hits 90 degrees, then we would have light only bouncing and none being transmitted. Now that won't work if we go from here to here, but in general, that's just the idea of total internal reflection. We use total internal reflection all the time, especially in fiber optic cables and in other electric applications. So total internal reflection, like I said, we'll just define it. When light passes from a dense medium to a less dense medium, so like I said, it wouldn't really quite work here. But if we had move the sun underwater, then we could have total internal reflection. So we're going to note this. When light is incident on an interface separating a we'll say a slower medium and a faster medium, and we'll note here that what I'm really saying is that N1 is greater than N2, then there exists a critical angle such that all of the incident light is reflected and none is transmitted. Oops, sorry. None is transmitted. And so we can show this diagrammatically and mathematically. So diagrammatically, and there's also some really nice demos that we made for you. So we could have maybe like a light source incident on a prism or something. So we might have something that looks like this. And we might have light entering this like so. And it will be incident, so we'll call this N1 and N2 such that N1 is greater than N2. So maybe N2 is air or something, and N1 might be like an acrylic lens or something like that. So there's a normal right here. And what we're saying is that none of the light will be transmitted out here. It will all be reflected inside of this N1 item. We know that this will be equal because of the law of reflection, but we want to say that in this case, no transmitted light and what we would say then is that theta I is defined as our critical angle, and so theta I we'll call theta C for critical, and we can use Snell's law to get an expression for this. And so this is total internal reflection. So no light leaves the acrylic item or the fiber optics cable or whatever it may be. So Snell's law was n sine theta I plus, equals n refracted sine theta R. And now we're going to say that we want the critical angle, so n I sine theta critical equals nr sine theta r, but theta r is not being transmitted. In other words, what really is happening is it's being transmitted 90 degrees, and so we don't see it. It's not being transmitted. So the point is theta refracted is 90 degrees. And if you recall from math, sine of 90 is just 1. And so ni sine theta c for critical is equal to nr, which is n2 in our case. And so this gives us an expression that sine of the critical angle must be n2 over n1. And so we could even do the inverse sine to solve for the critical angle if we want. But all the critical angle is the angle that the incident light has to be on the medium in order to be totally internally reflected and to not be transmitted. And a really critical condition for the critical angle is that the light must be in a more dense or a slower medium than the other medium that it is trying to be transmitted into. So this is a long one, so I'm going to stop here and I'll do a couple examples of refraction in particular in another video. Thanks for watching.